Lesson 3.3, Logarithmic Functions and Their Graphs. In this lesson, we're going to focus on converting between logarithms and exponentials and using those ideas to solve logarithms and exponential equations. We're not going to focus so much on the graphs in this lesson. The first thing we need to review in this lesson is how to convert between a logarithm and an exponential. The reason we can use this conversion is because logarithms and exponentials are inverse functions. So suppose we have a log base b of x equal to y, and the equivalent exponential form would be b raised to the y equals x. So the base of our logarithm becomes the base of our exponential. The value we're equal to in our logarithm becomes the exponent. The value of our log x is the value we're equal to in the exponential. So this is something you just need to remember because we're going to use these conversions when we start solving these equations. Below are a few basic properties of logarithms that are useful when we start simplifying. So if you can remember these, it makes the process a lot easier when you start solving these problems. If you have a log base b of 1, that's always going to be equal to 0 because in the exponential form, the base of our logarithm becomes the base of our exponential. The value we're equal to becomes the exponent. We know anything raised to the 0 power is equal to 1. Second property, log base b of b is always equal to 1. Again, relating this to the exponential form, the base of our logarithm becomes the base of our exponential. The value we're equal to becomes the exponent. If we have a value raised to the first power, that's just equal to itself. And then you can look at these last properties. Using the same idea shows you how we can quickly simplify certain logarithms. Now we're going to go through a few examples applying these different properties. So in example 1, we have log base 2 of 8. We want to find out what this is equal to, so we're going to set it equal to x. And now we're going to write this in exponential form. So the base of our logarithm becomes the base of our exponential. The value we're equal to becomes our exponent, now equal to 8. And what we're doing is looking at both sides of these equation. We want to rewrite this so we have the same base. So if I have 2 to the x, I know I can rewrite 8 as 2 cubed. The reason we do that is because if our bases are the same, they're both 2 now, that implies that the exponents must be the same as well. So we create a new equation where we get x equal to 3. And now we've solved that logarithmic equation. Example 2, we have log base 5 of 1/25. We want to evaluate this logarithm, so we set it equal to x. Now we can rewrite this in exponential form. So the base of our logarithm becomes the base of our exponential. So we have 5 to the x equal to 1/25. Just like we had in the last problem, we want to rewrite it so our base is the same on both sides of the equation. We have to be a little more creative in this problem to get it in that form. We're going to leave this left side the same, and we're going to work with the right side. I know 25 is the same as 5 squared. And now I want to get this value in the numerator. So I have 5 to the x equal to, if I move that to the numerator, my exponent becomes the opposite sign. So now I have it, so my base is 5 on both sides of the equation. That implies the exponent values must be the same. So we create a new equation. We get x is equal to -2. Example 3. We have the common log of the 5th root of 10. If there's no base written in, we know this is the common log, which is base 10. So again, we want to evaluate this, set it equal to 10. This is set it equal to x. If this is the common log, we have 10 raised to the x equal to the 5th root of 10. Now looking at this right side of the equation, the 5th root, we can rewrite that as an exponent value. So 10 to the x equal to 10. The 5th root is the same as an exponent of 1/5. Now our bases are the same. We create a new equation because we know the exponents must be the same. Thus we get x equal to 1/5. Example 4, we have log base 6 of 1 divided by the 5th root of 36. Again, we set this equal to x because we want to evaluate this logarithm. So this means we have 6 raised to the x power equal to 1 over the 5th root of 36. Again, we got to be a little creative in rewriting this problem. Our goal is to get it so our base is 6 on the right side of this equation. So we have 6 to the x equal to, first thing, if we have the 5th root, just like we did in the last problem, we can rewrite that as an exponent. So this is the same as 1 divided by 36 to the 1/5 power. And now we need to rewrite 36. We know 36 is the same as 6 squared. So we have 6 squared raised to the 1/5 power, which if we simplify power to a power, we multiply those values together. So we get 1 over 6 to the 2/5. Last step, we need to get this value in the numerator so that our bases are the same. So that would be equal to 6 to the negative 2/5 power. So now we have our value on the left and the right side. Both of our bases are 6. So we create a new equation. We get x is equal to negative 2/5. Example 5, we have an exponential. We have e raised to the natural log of 4. And this actually simplifies down to just 4. Okay, the reason this works is because what we started with, that exponential, that's the same as e raised to log base e of 4. This is the natural logarithm. It's very common. That's why we have a special notation we use for the natural logarithm. If we set this equal to x, now if we took this exponential and rewrote it in logarithmic form, this value would be equal to log base e of x, and then we would set that equal to this value we have here, which is log base e of 4. Since we have the same logarithm and base on both sides, that implies x would have to be equal to 4. We don't have to go through this step to show why this works. If we recognize that these basically simplify each other out, we're going to remain with just this value. Example 6, we have another exponential, 10 raised to the common log of 6. If you can remember, we talked about this earlier, the common log has a base 10. So just like the last problem, this is going to simplify down really nicely. This just equals 6. Similar for the last problem, we could rewrite this as 10 raised to log base 10 of 6 equal to x. Then if we rewrote this in logarithmic form, we would have log base 10 of x equal to log base 10 of 6. Again, we don't have to go through these steps. If we recognize right away that this is log base 10 and we have an exponential with base 10, those simplify, we're just left with the value of the logarithm 6. So to summarize this lesson, the main thing you need to remember or know how to do is how to rewrite a logarithmic function in exponential form and vice versa. Because when you're solving these problems, more times than not, you're going to be rewriting it in the opposite form in order to solve. So you need to understand how the base of the logarithm relates to the base of the exponential and how these other values correspond to each other.